Yeah, good morning, guys. So we will start with the further discussion, that is with respect to the real-time operating system. The session what was being concluded in yesterday's video. So we already discussed regarding the types of operating system, and we had a very brief idea regarding the two types of operating system. One was called as general operating system. Other one what we are discussing right now is real-time operating system. As I said you, general purpose operating systems are the ones in which the deterministic or the behavior of the system can be non-deterministic. And normally general purpose operating systems are used in a system where the response is non-critical. Even if the delayed or even if the system is going to give you a delayed response, that is not going to affect or that is not going to have that much or that is not going to be so much dangerous. When I speak about the other kind of operating system, that is real-time operating system, what you can see on the board or what you can see on the PPT right now, this particular operating systems are the one in which the behavior of the system should be very much deterministic. Whenever I say I am going to use a real-time operating system, the system should be able to respond to the inputs that come to the system in a given amount of time. If the system is not able to respond to that particular input in a given amount of time, then probably it is going to lead to an accident or it is going to prove dangerous to the environment where you are actually using an embedded system. That is why we call it as real-time operating system. Real-time implies deterministic in timing behavior. Real-time operating system services consumes only known and expected amount of time regardless of number of services. So no matter whatever number of services you have in that particular system, when you are operating a particular task or when a particular job is being done, the response of this particular job or the response of this particular task should be deterministic, no matter whatever number of tasks are queued or whatever number of tasks are getting executed. When it comes to a task of your concern, the system or your embedded system should be able to give the response in a given amount of time. This particular deterministic behavior is implemented using a certain set of policies and rules which are concerned with the time critical allocation of the system resources. So when you say that this particular task should be giving you the response in a given amount of time, the underlying resources what your embedded systems are having should be able to respond very immediately. That is what it says here. So real-time operating system will be having a set of rules and policies and principles which will make the underlying resources work very immediately. And this real-time operating systems normally decides which application should be running in order or which application should be given the highest priority and how much time is needed for that particular application to complete its run. So normally your real-time application will be or the behavior of a behavior of a real-time operating system will be deterministic just because of this particular two parameters. There are set of applications and principles which will say that what are the number of resources that has to be utilized in the given amount of time. Second thing is, in order to run that particular application, it will decide what is the time. What is the time that is needed in order to run that particular application. For example, if you speak about the Windows embedded contact, QNX, VxWorks, Micro, C or OS2, these are all the examples for your real-time operating systems. Or if you want to have a very real example, you can speak about the airbag system of your car. So as soon as there is a lot of stress that is happening on the body of the car, suddenly the airbags will open up. So if the airbags are not going to open up in a given amount of time, then obviously you know what is going to happen. The people who are sitting inside the car are going to be damaged. So normally the system which expects the critical response, you cannot use a general purpose operating system. You cannot say that, sir, my system should be giving me a critical response, or you cannot say that, sir, I am using this particular device for the medical equipment. Medical equipment means it is very critical, isn't it? So you cannot say that, sir, I'll be going with the general purpose operating system. In all those critical applications, you should be going with the real-time operating system itself. Fine. When I speak about the operating system, the ultimate thing what comes to my mind is kernel of that particular operating system. Similarly, when I speak about a real-time operating system, the kernel what I use in a real-time operating system will be named as real-time kernel. This real-time kernel, as I said you, my real-time operating system will be having a set of policies and principles, right? Very similarly, the real-time kernel is highly specialized and it contains only the minimal set of services required for running user applications and tasks. So please remember here, when you speak about your embedded systems will be of specific application. It will be of specific application. So when I say it is of specific application, your embedded system should be connected with only the limited number of devices, right? It may be the input devices or it may be the output devices. You cannot say that, or you cannot simply connect the devices which is of no use, because all these devices has to be run by the operating system, right? So normally in case of your real-time operating system, you will be connecting only the limited number of devices, and the services what are used to run this particular applications or task will also be limited. So my real-time kernel will always be specialized and it will contain only the minimal set of services or directories in order to run the given user application or task. So it is not overloaded, or your memory will not contain unwanted data or unwanted codes. It will contain only the codes and the data what is used to run that particular application. Suppose it contains unwanted data or unwanted application, then normally your system might spend some time in segregating what is the data that it requires and what is the code that it has to run. So it will contain only the data what it is needed. The basic functions of the real-time kernel very similar to the things whatever we studied previously. One is task and process management. We have studied about process management. One is schedule. Second one is task and process scheduling. Third is task and process synchronization. Fourth one is exception or error handling. Normally whenever I run a code, there will be errors or exception that will be occurring. So we need to check out how this operating system, or how good your operating system, or how good your real-time kernel is in handling this particular exceptions or errors. Memory management. How good is your kernel in managing the memory? Whether it is allocating the data and codes in the respective memory, or does it have anything special in order to allocate the memory. Next one is interrupt handling. How good your kernel is in handling the interrupts that are coming from the input devices and output devices. Last one is time management. Very important for me, because when I speak about the real-time operating system, my real-time operating system on the outset works in the given time frame. Within that given time frame it has to work, right? So time management is very important thing. So these are the 7 tasks what your real-time kernel is going to perform. So let's check them one by one. The first task or process management. So this deals with, so normally when you have a task or job to be done, the first thing what has to be done is the kernel should be doing the preliminary work, or when you are operating or when your embedded system is asked to do a particular task, normally there are set of tasks which has to be set up, or there are some preliminary settings that has to be done. So normal things what has to be done is memory has to be set up for a particular task in order to load the task code, or you need to load the code with respect to that particular task in the memory space, allocate the system resources, and also set up the TCB. TCB is called as task control block. We'll check up what is this task control block, and we'll check up what are the functionalities of this task control block, probably very immediate after this particular discussion, for the task and task process elimination and termination and deletion. So whenever a task has been assigned to your embedded system, now first thing what your kernel has to do is, kernel has to manage that particular task or process. How basically it does? It has to allocate the memory, it has to see where the code corresponding to that particular task has to be stored, it has to allocate the resources, it has to check what are the resources that are needed in order to run that particular task, and it has to also set up a TCB, task control board has to be set up. A task control block is used, see it's given here. A task control block is used for holding the information corresponding to the task. Task control block usually holds or usually contains the following set of information. So normally when a task has been assigned, or when the task has to be done by the embedded system, memory will be allocated, the code corresponding to that particular task will be stored in the respective memory. the resources corresponding to that particular task will be allocated, and after all these three tasks are being done, it will set up a TCB, or it will be setting up a task control block. Normally this task control block will contain a lot of information with respect to the task what it has to perform. So what are the information it is going to contain? First one is task ID. Task identification number is all about, let me say there are a lot of tasks to be performed. So task control block will contain the given task is to be done when. So that is what is your task identification number. Here it is 3, but in case of your system it might contain a multiple number because there will be multiple tasks to be performed, right? So TCB will be containing the task identification number. Task state. Task state is all about in what state the task is right now, whether it is in the ready state, whether it is in the abandoned state, whether it is in the waiting state, or whether it is in the execution state. The state of the task will, the information regarding the state of the task will also be given by your TCB. Task type, what type of task is it? Whether it is a real-time task, or whether it's a hard real-time task, or whether it is a soft real-time task. Hard real-time task means within the given amount of time the task should be performed. Soft real-time task means I can give you an allowance of somewhere like plus 2% or minus 2%, or whether the task has to be performed in the background. So type of the task information will also be contained in the TCB. Task priority. What is the priority of the task? Whether the task priority is 1, whether the task priority is 2. For example, let us say that some tasks are getting performed. Suddenly a task gets imported here, and you need to check what the priority of the task. If the priority of the task is 1, then all this task completion or all this task execution should be suspended and your task should get executed first. So that is regarding the task priority. Task context pointer. So this is with respect to the data with respect to the task what has to be saved, so that when the task gets executed, those tasks can be withdrawn from the memory where it has been saved and get executed. That is with respect to the task context pointer. Task memory pointers. Pointers to the code memory, data memory, and the stack memory for the task. So when your task gets executed, or when your task has been assigned to the embedded system, your operating system will be storing the code data in a particular memory. So they will have a pointers, right? So that where the memory pointers or where the pointers has to point when that particular task is getting performed, that is given by your task memory pointer. So that information is also given by your TCB. Task system resource pointer. So what are the resources that are needed in order to complete your task? So that information will also be contained by your TCB. Task pointers. Pointers to the other TCB. In case it's something like what, you are given with a particular task and this task has got a subtask to be performed. So what in between the performance of the task, your control should go to the other task, right? So that is what is task pointer. If there are subtasks to be performed within the task, that information where the pointer has to move from the main task to the subtask, that is what is your task pointer. Other parameters, whatever other information with respect to the task are also contained in your task control block. So task and process management is not an easy task, or it's not an easy job. It is a complicated job, because whenever your embedded system is performing a particular task, there are a lot of information what has to be contained or what has to be known. All those informations are contained in the task control block. The parameters and the implementations of the TCB is kernel dependent. The TCB parameters may vary across kernel based on the task management implementation. Quite obvious. So it depends on the operating system. So if you are using various operating systems, not all the operating system might contain the kernel, which might contain the TCB, which might contain all this particular information. So the TCB might contain various information depending on the kernel what you are using in the operating system. Not all the kernel should, or not all the TCB should contain all this particular data, but most of them, or 90% of the kernels, will give you all this particular information when a particular task has to be performed. That is what is your TCB. The second task what has to be done is task process scheduling. It deals with sharing the CPU among various task processes. A kernel application called .scheduler handles the task scheduling. It is basically an algorithm which performs efficient and optimal scheduling of tasks to provide deterministic behavior. This is about how you know. This is about, let me say there are 4 tasks to be performed. 4 tasks to be performed, and there's a CPU. So this 4 tasks will be scheduled in such a way that your CPU is utilized to the most. For example, let us say you have addition, subtraction, multiplication and division to be performed. And there are, for example, there are 4 blocks in the CPU. One is performing addition, one is performing multiplication, one is doing subtraction, and other one is doing division. So if there are 4 tasks to be done, what your process or task scheduler will do is, it will give individual task to individual part of the CPU, so that all the tasks will be performed at a given amount of time, which means that your CPU will be utilized very efficiently. This work will also be done by the kernel of a real-time operating system. So kernel of a real-time operating system will have an algorithm, and the algorithm is called a scheduler, and the scheduler will be scheduling the task or process so that your CPU or your processor will be utilized to the maximum. That is the second task what has to be done by the real-time operating system kernel. Third thing is taskbar process synchronization. This deals with synchronizing the concurrent access of resources which is shared among multiple tasks and communication between various tasks. So here what has to happen is, when a task has been assigned, this task might need some resources. Let us say that there is already a task which is getting executed. Let us say that this my entire system has got 8 resources. Okay, out of 8 resources, let us say that 4 are already being used by one of the tasks. If there are 4 resources left out, and if those 4 resources are sufficient in order to perform this particular task, your taskbar process synchronization will be done by your real-time kernel, which will allocate all this particular 4 resources to this particular task and get the task performed immediately. For example, let us say that your car has an ABS, your car has a let's say that airbag system. So I'm pretty sure the resources with respect to the ABS and the resources with respect to the airbag are comparatively different. So let's say that you are about to meet with an accident and you are suddenly applying the ABS. So as soon as you apply the ABS, let's say that due to some problem your ABS didn't get applied. So now what should happen is the airbag should open, right? So the system with respect to the airbag system cannot wait for some amount of time. It should open suddenly when the car meets with an accident. That's what I said here. The resources with respect to the task, if they are available, they should be given to the particular task in a given amount of time, so that the multiple tasks will be getting performed within the same time, so that the communication happens between the various resources. The communication with respect to the ABS has also happened, and the communication with respect to the airbag system has also happened here. That is what is taskbar process synchronization. Error bar exception handling. Quite obvious, right? When a task is getting performed, you cannot expect your task to be having 0 error. You cannot expect. There will be an error. There will be lot of errors which will be occurring in the system. Some of the errors, very common errors, are insufficient memory, timeout, deadlock, deadline missing, bus error, divide by 0, unknown instruction execution. These are some of the errors and exceptions which are very frequently executing, or which will be very frequently happening in a embedded system. When this particular errors happen in your embedded system, how this particular errors are sorted out, or how this particular errors or exceptions are handled. They are actually handled by the kernel. They deal with the registers, or they deal with registering and handling the errors occurred or exception throws during the execution task. Your task is already under execution. When the task is under execution, all these particular things will happen. Error or exceptions can happen at the kernel level service or the task level. For example, deadlock is an example for the kernel level exception, whereas timeout is an example for the task level exception. Deadlock is something like your task is getting performed very properly, and suddenly it's like hang up. Your system gets hanged up. You press any button, you press any key, the system is not working. That's called as deadlock. So how should that particular system or how that particular error or exception should be removed off? Or maybe there are some issues where the number is getting divided by 0. When it is getting divided by 0, it's an error. It's a 0 divide error. So normally how those particular tasks are or how those particular errors are actually getting sorted out. Errors or exceptions can happen at the kernel level services or the task level. Deadlock is an example for the kernel level execution, whereas timeout is an execution or is an example for the task level. What is deadlock? Deadlock is a situation when a set of processes are blocked because each process is holding a resources and waiting for another resource acquired by some other process. So let's say that task 1, task 2 and task 3. So this needs 4 resources, this needs 4 resources and this needs 4 resources. One of the resources is common for all the 3 tasks. So let's say that all these 3 tasks are getting executed simultaneously. Now one of the resources is common for all the particular tasks. So what should happen? None of the tasks will be getting that particular resources. That particular situation is called as deadlock. Now your kernel should be able to sort out of this given task who is having the highest priority. So it will go to the TCB task control block and it will check out which task is having the highest priority. So that particular task will be given with that particular resource and the remaining task will be asked, you wait, so that he finishes off his work and he will give you the resources what you need. This is how your kernel is actually going to sort out the issue, or this is how your kernel is going to handle the errors and exceptions. There are timeouts. Timeouts in the sense you expect a task to be completed in 5 seconds. Your task is not getting completed in the 5 seconds. So what your kernel will say is fine, you wait for 2 more seconds. After 2 more seconds, your kernel will say timeout. It's done. You cannot wait for anything more. Let's start the task again. But again here there is a risk that if a system is very much critical, timeout cannot occur. Timeout and retry cannot occur. See, timeouts and retries are the 2 techniques used together. The task retries an event message certain number of times. If no response is achieved after exhausting the limit, the feature might be aborted, which might ask you to restart the things. The operating system kernel gives information about the error in the form of API, or it's in the form of you had something like system call, right? System call, in sense it displays on the monitor. It's an error. It says that no, that's not going to happen. Airbag is not going to open up. It's going to show an error. Or your AirBS is not working. It shows an error, which means that your kernel is not able to sort it out. But 99% of the times your kernel will be able to sort it out. So kernel should be able to sort out this errors which are due to, or sort out the errors and exceptions. Next is memory management. Memory management is also important work, because when you start up a task, normally you need a particular amount of memory in order to store the data, in order to store the code, and also you need some amount of stack, right? You need some amount of stack. So all this particular memories has to be allocated by the operating system. So here the memory management function of the real-time operating system kernel is slightly different compared to the general purpose operating system kernel. Very obvious. So when I speak about real-time operating system and general purpose operating system, the memory allocation between this is slightly different. My general purpose operating systems goes with the dynamic allocation. Dynamic allocation means it checks what is the amount of memory that is needed to store the data, what is the amount of memory that is needed to store the code, and what is the stack memory that is needed. This is called as dynamic allocation. Whereas in case of your RTOS, you go with the block allocation. You go with the block, it's given here. In general, memory allocation time increases depending on the size of the block of memory needed to be allocated and the state to be allocated to the state of the allocated memory block. RTOS achieves predictable timing and deterministic behavior by compromising the effectiveness of the memory allocation. So actually if I compare, dynamic memory allocation is one of the best. But if I go with the dynamic memory allocation, normally it is going to consume time. Your real-time operating system should give you the response in a given amount of time. You cannot waste your time in allocating the memory. So what I go with is, I go with the block allocation. So what happens here is, RTOS kernel uses blocks of fixed size of dynamic memory and the block is allocated for the task on the need basis. So your real-time operating system do not calculate what is the amount of memory that is needed for a particular task. It would have already blocked or it would have already divided the memory into certain blocks. So when a task has to be performed, your real-time kernel will say, fine, see there is a memory block which is available, you can occupy that particular block. It doesn't calculate what is the amount of memory that is needed. If it keeps on calculating the memory, it will take a lot of time, right? So it will simply say that block is available, so you go and occupy there. And this particular block is called as free buffer queue. Free buffer queue means space may be sufficient or there may be space which is extra. That is what is called as free buffer memory. Most of the real-time operating system kernels allows tasks to access any of the memory blocks without any memory protection to achieve predictable timing and avoid timing overloads. As I said you, memory allocation, I am not going to waste the time here. Neither I am not going to give any kind of protection to the memory here. So your task has to be performed. There are various blocks here. Your tasks are allowed to access all these particular blocks, whichever blocks. And the block which contains the data or the code corresponding to that particular task will get executed. So protection is minimum here. Some commercial real-time operating system kernels allow memory protection as optional and kernel enters a fail-safe mode when an illegal memory access occurs. Some of them, not most of them. Some of them does that. For example, your task and the code is located here. Suppose if the task tries to access this particular memory block, in the screen it will show that it is fail safe mode. Says that memory access is failed because the code corresponding to that is present here. The memory management functions a block or memory management function a block of fixed memory is always allocated for task, just like what I explained to you on need basis, and it is taken as unit. Hence there will be no memory fragmentation issues. So separate tasks, separate blocks. If it is dynamic allocation, what happens? There are chances that the code corresponding to task 1 might be overwritten on the task 2. So if task 1 has to be performed again, then there will be memory fragmentation. Data is missing because it's already overwritten. So that might happen in case of your general purpose operating system kernel. So what your real-time operating system kernel does is, it will say this house is for you, this house is for you, this house is for you. And whenever the wrong person goes to a wrong house, he will say that memory access failed. That is what is memory management. That is how the memory has been managed in case of your real-time operating system kernel. Interrupt handling. So I need not explain this to you at all. You know what are interrupts. Interrupts are nothing but calls given by the input and output devices. So when multiple input and output devices are giving calls to the CPU or to the processor, every call has to be processed, right? So your operating system will make sure which call is having highest priority and which is having the lowest priority. Deals with handling the various interrupts. Interrupts informs the processor that external device or an associated task requires immediate attention of the CPU. Just like what I explained to you. Multiple people are going to ask the service of the CPU. Your kernel has to sort out who will be given with the service of the CPU first and who will be given with the CPU later. This interrupts are actually categorized into two categories. One of them is called as synchronous interrupts and other one is called as asynchronous ones. Synchronous interrupts are the ones which are given by the devices with respect to the task that is getting executed. Interrupts which occur in sync with the current executing task is known as synchronous interrupts. So let me say that you are typing something. Okay. So normally when you are typing something, you have a keyboard. So whatever interrupts come from this particular keyboard, because the task that is getting performed is typing. So whatever inputs are coming from this, I can call this particular interrupts as synchronous input because the interrupts is synchronized with the task. Whereas there are interrupts which are not synchronized with respect to the task. You are typing something and there is something like you need to take a photo. You are typing something and you need to take a photo. Then this particular interrupts are called as asynchronous interrupts. Now my question is, so during typing, if the photo has to be clicked, what will happen? That depends on the kernel. If clicking the photo has got the highest priority, then obviously your kernel has to suspend this typing task and he has to immediately go with the clicking the photo task. That is what it happens here. See, here something else is given. Divide by 0, memory segmentation errors are the examples of the synchronous interrupts. For synchronous interrupts, the interrupt handler runs in the same context of the interrupting task. Here, interrupt which occurs at any point of execution of the task and are not in sync with the current executing task are called as asynchronous interrupt. As I said you, typing is a synchronous one and clicking a photo is a synchronous one. But again, execution depends on the priority. It depends on the value that is present in the TCB. Interrupts which occur at any point of the execution of the task and are not in sync with the current are called as asynchronous. Fine. Timer overflow interrupts, serial data reception transmission interrupts. See here, serial data reception transmission interrupts. Clicking a photo, your camera is ready to give some input and you have to process that particular input and you have to send it out because you are doing something else, you are typing something. In between you have to do some other work. Those are all the examples for the asynchronous ones. How does your kernel sort it out? Same things. Priority levels can be assigned to the interrupts and each interrupt can be enabled or disabled individually. So kernel will go to the TCB and he will check what is the priority of the interrupt. If the priority of the interrupt is high, then that interrupt will be serviced. If the priority of the interrupt is low, then that will be masked away. He will say you wait for some time. And this particular task is called as nested interrupts. You call this particular architecture as called as nesting of the interrupts. Nesting of the interrupts means, fine, first one, task 1, after that task 2, after that again task 3. So nesting, which is having the highest priority will have the highest nest, which is having the lowest will have the lowest nest. That is what is called as nested architecture. Time management. One more important thing, because I said you, time management is everything for me in case of my real-time operating system kernel, because I want the task to be performed within the given time. Accurate time management is essential for providing precise time response or reference for all applications. The time reference to kernel is provided by the high resolution real-time clock hardware chip, hardware or hardware timer. So you know your work has to be completed in 5 seconds, but your kernel should know, right, how that when that 5 seconds gets covered up. So there should be some clock inside, and the clock what you have inside the kernel is called as RTC, that is real-time clock, or you can call it as hardware timer. So that acts as a reference from the moment you have started the work and from the moment you get the output. The hardware timer is programmed to interrupt the process by controller at the fixed rate. This timer interrupt is referred as timer click. You call your timings as second, right? You call your timings as second or minutes or hours, right? Very similarly, the count in case of your timer of the kernel or real-time operating system is called as timer tick. This timer tick is taken as the timing reference by the kernel. How many timer ticks, within how many timer ticks you need to finish up the task? How many seconds you have to finish up the task? So you cannot say it in terms of seconds. When I get into the embedded system or when I get into the kernel of a real-time operating system, that is given in terms of the timer tick. The timer tick interval may vary depending on the hardware timer. So you cannot say that 5 timer tick of one embedded system will be equal to the 5 timer tick of the other embedded system. They depends on the various operating systems or various kernels of the operating system that is given here. Usually the timer tick varies in microseconds range, normally in terms of microseconds. Let's check out that. See here, if the system time register is 32-bit bytes and the timer tick interval is 1 microsecond, the system time register will reset in. Reset means time out, when it will happen. 2 to the power 32 microseconds, 10 to the power minus 6, divided by hours, minutes, seconds. So it will set in somewhere around 0.0497 days or somewhere accurately in 1.19 hours. If the timer tick is 1 millisecond, then you have to check. For 32-bit register, it will reset in 50 seconds. So this is how normally the time will be managed. This is how your kernel will time. See, this is the timer tick. Within this timer tick, you have to give the output. If that doesn't happen within this timer tick, I will declare a timer out. That is what happens in case of your, say it's given a lot of things with respect to the things are given here. The timer tick interrupt can be utilized for implementing the following action. Save the current context. So what is the time duration within which the context has to be saved? Increment the system time register by 1. Update the timers implemented by the kernel. Activate the periodic tasks which are in the idle state. So all the work which are happening inside the kernel, which is actually running the embedded system, are all running with respect to the timer tick. So timer ticks will be given. Within this timer ticks, it has to be reset. Within this timer ticks, you need to get the output. Within this timer tick, the data has to be stored in the memory. Within this timer tick, the data has to be deleted or it has to be terminated. So all that will happen with respect to the timer ticks. Invoke the scheduler, delete the terminated task, load the context. All the works will happen with respect to the timer ticks which are specified within. So probably this is with respect to the various tasks that are performed by the real-time kernel of a real-time operating system. So you need to know all these tasks individually, or you people should be able to at least explain the side headings, and you should be able to explain the functionalities of each and every block at least by 10 lines or a paragraph, because they will normally ask you what are the different functionalities that are performed by your real-time kernel. Fine. Let's wind up the session right now. We will have the discussion regarding the continued part or other topics in the coming video session.